What specific problem does your proposed method address regarding inference efficiency in I, and why is it particularly crucial in the context of large language models?
Our proposed method addresses the critical issue of memory-bound performance during the decoding phase of large language models, LLMs, specifically the inefficiencies associated with the multi-head attention, MHA, mechanism. The sequential token-by-token decoding process leads to significant latency due to the large key value, KV cache that must be fetched from high-bandwidth memory, HBM, which can quickly exhaust available memory and reduce GPU utilization. This inefficiency is particularly crucial for latency-sensitive applications, large batch inference and multi-step reasoning tasks, where prolonged latency can severely impact performance. By introducing hardware-efficient attention variants like grouped tied attention, GTA, and grouped latent attention, GLA, we significantly reduce the KV cache size while maintaining model quality, thereby enhancing arithmetic intensity and overall inference speed. These improvements allow for better scalability across devices and more effective utilization of modern hardware, which is essential for deploying LLMs in real-time applications.
How does the proposed method, specifically grouped tied attention, GTA, operate? Can you break down the algorithm step by step, including details on how it ties KV representations and how it utilizes grouped query heads?
Group tied attention, GTA, operates by unifying the key and value KV representations into a single shared state, which is used by small groups of query heads. The algorithm begins by grouping query heads, where each group shares one distinct KV head, thereby reducing the overall KV cache size. GTA further ties the key and value projection parameters, creating a tied KV state that matches the shape of an individual key or value vector. In this setup, the value path utilizes the full dimensionality of the tied KV state, while the key path only uses the first half of this state as the unrotated half, with the remaining portion derived from a separate one-head projection of the hidden state, which is broadcast across all groups. This design effectively reduces memory transfers, roughly doubles the arithmetic intensity, and halves the KV cache footprint compared to its grouped query attention GQA counterpart, while maintaining comparable model quality.
Can you provide a simple example of how the grouped latent attention GLA algorithm processes a sequence of tokens, illustrating the key steps in the attention computation?
The grouped latent attention GLA algorithm processes a sequence of tokens by first compressing the tokens into latent heads, each with a dimension of d_c equals 2d_h. For instance, if we have two latent heads, as in GLA2, the algorithm partitions the query heads into two groups, allowing each latent head to reconstruct distinct key and value features for its assigned query heads. During decoding, each tensor parallel TP rank computes local attention using its assigned latent head and query group, applying its slice of the output projection. This process involves performing attention calculations directly on the compressed latent representations, which reduces the overall memory footprint and enhances efficiency. Finally, the results from each TP rank are combined through an all-reduce operation to produce the final output, ensuring that GLA maintains high arithmetic intensity and efficient parallelization across devices.
What theoretical advantages does GLA provide over traditional multi-head attention and the other existing methods like multi-query attention, MQA, and grouped query attention, GQA?
Grouped latent attention GLA offers several theoretical advantages over traditional multi-head attention MHA, multi-query attention MQA, and grouped query attention GQA. Firstly, GLA achieves a higher arithmetic intensity by compressing tokens into latent heads, allowing for efficient parallelization without duplicating the KV cache across devices, which is a limitation in MHA and MQA. Secondly, GLA maintains model quality comparable to MHA and MLA while having the KV cache footprint per device, thus reducing memory traffic and improving decoding speed. Additionally, GLA's design allows for better scalability in distributed settings, as it can effectively partition latent heads across devices, mitigating the memory bottleneck seen in MHA and GQA. Lastly, GLA's architecture enables it to achieve up to 2 times faster performance in speculative decoding scenarios compared to existing methods, demonstrating its efficiency in practical applications.
Describe the validation methodology you employed for testing your proposed methods. What datasets and performance metrics did you use to demonstrate the effectiveness of GTA and GLA?
To validate the effectiveness of the proposed methods grouped tied attention (GTA) and grouped latent attention (GLA), we conducted experiments on 4 model scales: small 183M, medium 433M, large 876M, and XL1 471B parameters, using the FineWeb-Adu 100B dataset. We evaluated validation perplexity on 100M tokens from this dataset, as well as on 4 additional datasets: Wikipedia, C4, Colossal Clean Crawled Corpus, portions of Red Pajama V1, and Cosmopedia, each also evaluated using 100M tokens. The performance metrics included validation perplexity and average downstream accuracy across various benchmarks, such as SciQ, OpenBookQA, and MMLU. Results indicated that GLA achieved lower validation perplexities compared to MLA, while GTA improved upon GQA, demonstrating comparable or superior performance in downstream tasks. Specifically, GLA2 and GLA_Q2 achieved the lowest average perplexities across the evaluated datasets, confirming the effectiveness of our proposed attention variants.
What limitations did you discover in your approach, particularly regarding scalability and potential quality trade-offs in larger models? And what future research directions do you propose to address these challenges?
In our approach, we identified limitations related to scalability and quality trade-offs, particularly when increasing the group size, G_Q, in attention mechanisms. While raising G_Q enhances arithmetic intensity and reduces the KV cache size, it can lead to diminished parallelization capabilities, as excessive duplication of parameters across devices occurs, ultimately limiting the benefits of model parallelism. Additionally, although our grouped latent attention GLA maintains comparable quality to multi-head latent attention MLA up to the 1/471B scale, the potential for quality degradation exists when scaling to larger models, especially if the number of latent heads is not optimized. Future research directions include evaluating larger-scale models with more latent heads while keeping the head dimension fixed, as well as exploring the application of partial rope in fewer layers to mitigate the KV cache footprint and enhance performance. These studies could provide insights into balancing quality and efficiency in high-capacity models.